Alright guys, welcome back to Diag. Today's vehicle is a 2017, I believe, Honda CR-V. And first and foremost, forgive the background noise. I've got a couple fans running. It is summertime, so it's kind of hot. So hopefully at least this portion will come out clear. The reason why this vehicle is here, it's been brought over from my friend's shop. He's asking me to take a look at it and possibly do the work if I can find something wrong with it. The customer had brought it to Honda, and based off of a startup noise and I think noise at idle possibly and trouble codes, they recommended to replace basically all of the timing components in order to basically, as they said, have the engine not blow up. So customer brought it to my friend's shop with whatever the symptoms are and whatever Honda told them, and so now it is here. I've let it sit for about a couple hours. I want to get it in a cold start situation, try to duplicate the rattle noise. Now this is not uncommon. If we have either a chain issue, a tensioner issue, or a cam phaser issue, we can get some rattling noises. So I want to try to capture that and try to see where the noise is coming from, if I can get a noise to happen, and we can try to verify any of the trouble codes and see why they might be popping up. Alright, so the health report is done. I'm going to go ahead and turn the key off because this battery is low. Alright, so we have P0341, which is cam sensor A and crank sensor incorrect phase detect. So basically a correlation code with the cam crank. Let's see. Sensor B range performance, cam sensor B, and then and then those repeat. So basically looks like it's describing that we've got a cam crank correlation and possibly the exhaust variable cam timing is not operating or hitting its targets as it would like. Okay, so I'm letting the battery charge, and I'm researching a little bit with the trouble codes. And first, as you can see there up top, we are checking out the 0341, which is the intake correlation with the crank, cam crank correlation for the intake side. The one thing that I ended up finding here in the service information is that basically the deviation point basically of base timing, because if you look down here, while the variable valve timing control is not activated, and then forgive me, there at the bottom for enabling, if you look right here, the with the VTC system not operating, so it's related to basically base timing. And then here on the bottom, where are we? Where it deviates basically for at least 10 degrees or more for that 4 seconds. So that's the for description for the intake side. And next we look for the same thing for the P0366, which was for the camshaft basically exhaust side, and if you remember, I was thinking, meaning that it was probably not controlling the variable cam for the exhaust correctly, or not reaching its point, or some to that extent, based off of the description. But to my surprise, if you look over here, for the service information, we get the same exact description over a time while the variable valve timing control is not activated, and then here also again with VTC not operating, and it's the same spec of 10 degrees at least or more. So two different descriptions could be a little bit misleading, but the both of them are the same exact enabling conditions for setting those two different trouble codes, and it's basically telling us that both the intake and the exhaust cams in relation to the crank are at a minimum of at least 10 degrees off of their specified base timing set point. Alright guys, so as you can see, I've got the scope set up, got quite a few channels going. Let me try to explain as far as what I want to look at and why. I've got all my basically electrical connections made here at the computer, and then on top of that I've got obviously the amp clamp, so I want to look at the starter draw, and then I've added these noise detection clamps basically. I've got one there, here's my other one, and then I've actually got one right down there on the lower timing case cover right next to the timing chain tensioner. So as I told you, this has and experiences a kind of a rattle noise during startup. So I want to try to determine a couple things. So we've got the trouble codes that we are chasing, which is basically intake and exhaust timing not being correct. Then we've got the symptom of the noise at startup. And so here I am going to monitor the crankshaft sensor, intake cam, exhaust cam. I've got ignition cylinder 1 sync, and then obviously starter draw. And then here I've got a clamp on the lower timing chain tensioner, one up by the intake cam phaser and one by the exhaust cam phaser. I want to see if we can try to determine where the highest rattle noise is coming from, or any of the noise coming from during startup. And then I want to watch all the cam signals to see if the cams are moving, meaning like phaser's not locked or whatnot, and so on and so forth. So that's my setup. That's what I've got going on. Today, right now, is the next day. So I've let it sit overnight. I've not started it. I actually charged the battery overnight and this morning as I got all set up. And so this will truly be the first startup. Hopefully it's basically, let's call it the loudest, as we assume oil has drained down into the sump, and then we'll see what kind of results we get. There's a couple tests that I want to do. Normally, to check the base timing and stuff, I do a crank no start. That's where you're checking your base timing with no interaction of anything, so on and so forth. But I don't want to do a crank no start and build up oil pressure, and then when finally start it and run it, get rid of the rattle noise because we've built up oil pressure from cranking and no start. So I think I'm going to do a start up to get the noise going first, and then later I'll do a crank no start. Alright, so we got our capture there. We're going to go over that here in a minute. But right now I've disabled the vehicle from starting. And it has sat for maybe 2 hours after the last startup and run. So let's see what it looks like just cranking. So we'll start the scope. Alright guys, so what we have here is a capture of the first startup, the cold startup that we just took. And we do have a lot of things going on here all at once since we're monitoring a ton of stuff. I've moved some of these here towards the bottom. This is going to be our cam sensors, crank sensor, ignition, so on and so forth, which we can take a look at that here in a little bit. Right now, since we're doing the first cold startup, we want to try to concentrate a little bit more up top on these that I've got on the top of the screen. These are going to be basically kind of like the, let's call it noise detection. And so if you remember, we are monitoring the tensioner down at the bottom, the intake phaser and exhaust phaser. So the way I've got these laid out is that this purple one will move to the top. That's the tensioner. That teal is the intake, and then the other kind of pink purple, that's going to be our exhaust. And right off the bat, if we take a look just at this kind of raw, far off point of view, the way that this works, these captures work with the noise detection, is the more, let's call it solid-ish and higher points that it reaches means that the amplitude is higher and stronger, which equates to basically picking up a louder noise. And so if you look towards here, this area, this one down here seems to be still more solid, let's call it, as opposed to those two. Now this is when we first started the engine and we went on idling. And so we want to take a look at these three areas again. So let's zoom in, and even here right away, we're able to pick up one that looks to be distinctively more higher in amplitude. Again, this one down here, which is the over on the exhaust phaser area. And here zoomed in, you can tell definitely one is standing out way more different than the others. It's having a continuous repetitive amplitude occurring. Definitely compared to those, I would say that the exhaust is standing out. Now again, we're trying to take a look at this to determine if see if we can determine where the source of the noise is occurring. And this is what we're doing, what we're using, seeing if we could pick anything up. And sure enough, here, zoomed in, idling, this is a clear shot of the source of the noise, which is going to be right there in the exhaust area. Okay, so now we move on to this capture we've got here in front of us. This is the one of just the cranking no start. Again, this one I'm going to use to try to verify a couple things all at once with this one single capture. Obviously, the vehicles come in with those trouble codes, and so now we're going to put to use those cam and crank correlation ones, because I want to see what the base timing is compared to a known good, because of the code setting criteria is basically tattletaling, complaining about the timing being off without variable cam timing actuation. So it's referring to base timing, which the best time for me to check it, or I like to check it, is just at cranking. So we're going to use cam crank to watch that and compare. And again, out of curiosity, to see if we can capture any type of noise difference in those three areas that we just saw in the previous capture where it was idling. So let's zoom in here at a first crank up. And for right now, let's look down at the noise captures. So let's continue to kind of move forward. Let's zoom in a little bit more and continue on as we crank. So this is continuous cranking, and We are picking up noise in both what looks to be the lower tensioner area, a little bit of noise in the intake area, and then some noise again. Looks a little bit more prominent compared to down at the bottom here in the exhaust area. So both cranking and idling, this guy in the exhaust area seems to stand out with providing us some higher amplitude noise that we are capturing. Again, we're trying to do this to see if we can sort of pinpoint from the outside with just scope captures, if we can find out what possible parts we're going to need to try to get a better idea of what's going on. So as of now, the exhaust area seems again to be giving us some trouble as far as providing higher noise. So as far as the noise, I think we're gonna have to pay some close attention to the exhaust phaser. Not too sure right now during cranking if we should pay a great deal of attention to the timing tensioner, which I mean, naturally, when we go in to do any type of work there anyways, the tensioner will get replaced. So I'm not too worried that at cranking we're picking up some noise there. But the fact that always the exhaust is giving us something. And again, keep also in mind, these could be picking up, let's call it echoing chatter noise from wherever the source is creating it. And so these again could be possibly showing up due to if the exhaust is the creator of the noise. So that's what we're doing, cranking and running, trying to see what is the common denominator. And I keep beating up this dead horse, but it seems to be again the exhaust area. So with that, let's now move forward to taking a look at our timing issue, see if we can depict anything about the condition and or trouble codes. If you remember, I also added my ignition cylinder 1 sync and the relative compression e-starter current draw, which is here down at the bottom. And so normally there's times where you can use the relative compression to try to determine if we've got a timing issue. And if you were to, on this particular vehicle, if you were to tie yourself to just doing an RC test with a sync to determine if you have a timing problem, I would almost say that you would be lost or could be incorrect, as it seems to be displaying as if the engine is in time. And so that's part of why I wanted to capture this, because we have timing codes, and my curiosity wanted to see where the ignition lands during cranking, if this would be a viable test. And so after seeing this captured here, it would definitely assure me that this would be an incorrect call to determine if timing is off. So there's the shot of that. Now we will use the cam and crank, and let's see, we'll bring up the ignition sync a little bit higher. And of course you cannot determine based off of this unless you have a known good in order to make a call. As far as the channels go, clearly the blue is our crank sensor signal, our green is going to be our intake cam sensor, our yellow is going to be our exhaust cam sensor. Now, in order to find a known good, I normally like to go here on Diag.net, and in the search I ended up finding this, and so this here can be a viable source in order to attempt to find some known goods. And this here obviously is just a picture, screenshot. It's not the file. Sometimes people do post files on there, but I think this will be good enough for me to use. We've got all the same channels that we have in order to make a call. Obviously, ignition, cylinder 1, exhaust sensor, cam sensor, and crank. Here at the bottom is our sync points for our crank sensor signal. And so what I am going to use, I always try to find an identifiable point in the waveform. And it doesn't matter where, it's just something that works for you or easy on the eyes or something that you can relate to both waveforms. For me on this one, I'm going to use as a reference the ignition sync. Now, one side note or thing to look out for, and the gentleman on this one did not specify, but it sometimes can be important or needs to be important to state whether the waveform that's posted, if it's cranking or idling, running, revving, so on and so forth. I don't know if this one is cranking or running, but for right now, I'm just going to use this as a soft guide. So ignition number 1, let's compare it to the exhaust and just pick something out. We're going to say that the trigger point happens at basically a dip point. It's not synced correctly, like in line. Close enough, it's a little off, but it's close enough to, if we were to drop this, it would fall in an area where we'll call it a dip point. Now, the exhaust cam does not have an identifiable type of teeth pattern, it's just repetitive. So we're going to call it again to where the ignition of one would dip down into one of these gaps with the exhaust. And so now we take a look at our capture, and here is our ignition sync, and it's off to the right, and here is that dip on the exhaust trace. Again, the dip. And so our ignition is not falling within that area in the exhaust waveform. And so next, naturally, we're going to try to compare it to somewhere on the intake trace, and let's kind of call it that the down point of the ignition trace, again, it's not exact, but let's call it that it lines up with this uprise of the first big tooth. So somewhere in that region. And another reference point is this sync gap on the crank sensor, and where this falls is somewhere, just generalizing, let's call it the third tooth over. That's where it falls, and then here you can see that again. Let's call it the third tooth, and the ignition kind of close to that uprise. And so now if we look at ours, our drop point of our ignition is again more to the right from the uprise of the intake cam signal of that first big tooth. And then the other tattletale point is, it's, let's see, 1, 2, 3, 4, about the fifth tooth over from the sync gap. So with that there, with these cam crank signals compared to the known good, we are seeing where our trouble codes are being generated as we are looking at base timing at cranking, where the chains are set, where they sit, where they're always normally at before any type of attempt of variable cam timing control, and they are set and sitting at an incorrect point compared to a known good, and that's why we get our trouble codes. So we've got cam and crank correlation incorrect, so both cams compared to the crank are sitting off from where they should be, and we've got loud noise being picked up in the exhaust cam phaser area. Okay, so last thing that I want to do is basically check the variable cam timing, see if we can get some activation or if it's stuck. And I'll show you here in a minute. Off camera, I cleared the codes, I cranked it, started, and almost right away the codes came back. And so what I am doing is, the solenoids are power fed control, so all I'm doing is tapping the VTC solenoid power supply with some power, and maybe you'll be able to hear. So I'll activate the exhaust ones first, and ready. There, and then the intake side. So it sounds like the exhaust is a little bit louder, but both are clicking. And so what I will do is run it at idle and activate it, see if we could get some cam movement. Alright, so I'm going to do the exhaust side, and I've got an amp clamp so that way we can tell when we activate it. You hear almost stall, and that was on the exhaust side, and I held it for a little bit longer than I did before. I'll do that again. Alright, and I'm going to tap quick on the intake. Alright. So we'll go ahead and pause it and take a look at the amount of movement, if we have movement, which we're definitely going to have movement, so that's sort of a good sign. And I say that we are because you can hear a tone in the engine change, which clearly is telling us that the phasers are moving. So let's just take a look. And just to show you, we'll go ahead and clear the codes. We'll read. So no codes. Cycle the key. And we'll do a crank start and reread it. Remember, as far as the code setting criteria, both for intake and exhaust, it's basically saying base timing is off 10 degrees or more, and it doesn't need to activate the variable cam timing. So we'll go ahead and start it up, and let's read. Alright, so that one doesn't matter. Alright, so right away we've got our intake and exhaust codes coming back. And so lastly, let's take a look at this waveform here. This one's going to be kind of an important one, as we're trying to, at this point, determine to see if our phasers are actually, let's call it, providing a movement that they need to when activated. That'll tell us how basically the internals of them are working, if they aren't working. Again, kind of concerned with the exhaust side, being that we keep capturing higher noise in the exhaust area. And again, this can be a big cost deciding factor, as some phasers in some vehicle brands are very, very expensive, and so it can be a very big changing factor when you're estimating a job, depending on the customer's ability to afford the type of repair that is needed. So we are gonna take a look after activation of the exhaust phaser first, and then the intake, and we're gonna watch our cam sensor signals per each phaser to see if those sensor signals move. As far as the capture goes, this again is our noise stuff, ignition. The one that we're gonna pay attention to is here in this gray. I've used it as a sync basically to find a point in our cam sensor signals as to know when I activate it. So that's the area I'm going to look at during activation, and so that's the amp clamp. And I've got two activation points for the exhaust first, and then two activation points here for our intake. And so I'll just use that as sync point in the waveform, to look at the correlating cam sensor signal. So beforehand, meaning before the activation, let's take a look at our exhaust waveform. And it's going to be a little difficult because, again, there's not an identifiable point really in the exhaust teeth pattern. So we'll just try to figure something out. So if we move the intake downwards and bring up the exhaust up close to the crank, we're going to use the crank as our second reference point to see or watch if there's movement. And for now, let's call that one of these teeth. We'll use the sync point, the gap, as the reference point. Let's call it as this downward point of the tooth pattern happens right at the first tooth after the gap. We'll use that as our reference point. And so, with that, let's go over to our activation point. Now, I've done this in other demonstrations. Despite the fact that we electrically are seeing and know we've activated the control solenoid, you still have to wait for oil movement, so there's some latency as to when the cam will actually move. You can't expect it to happen right away. It's not, it's not the speed of light. So even at this point, obviously just before it, we're still lined up. And then here, there has been enough latency to we did move. So from one cycle to the very next after activation, we see movement. There has been enough movement of one tooth. And so let's continue on. Now that is sort of a good sign as far as telling us how things are intact. And so the next point, we've moved another tooth. And so hopefully, let's make this a little more visible for you guys. So there we go. And let's continue on during the whole activation point, which if this gray line is still present, we're still in our activation point. So let's go to the next cycle. And again, looks like we've moved further another tooth. And we're still activated. And let's see. Looks like, again, further, possibly another tooth. And we are still in our activation point. I think another tooth. Let's verify. 1, 2, 3, 4, 5, 6. So let's call it 6.5. We haven't reached the 7th one. I think I lost count, so let's go back. 1, 2, 3, 4, 5. Okay, so we're at 5.5, and we go to, let's call it 6.5. At this point, and let's see, we're still activated. We're still activated. Let's see, 1, 2, 3, 4, 5, 6, 7, 7.5. And that's where we dropped off. So we have moved the cam sensor signal 7.5 teeth towards the right. So we have our movement is in the direction of delay or retard of the exhaust cam shaft. I would say that our phaser is able to do its movement. Now, let's see, we were at 7.5. This is the very next cycle. So we've stopped oil from going to it, and now we're at 1, 2, 3, 4, 5, 6. So we've already dropped back. And let's double check and see if we can get it back to its starting point, which is that first tooth. That's going to give us our full motion of full retard and full starting lock point. Now, a lot of these phasers will rattle if they don't lock. So let's see if we get it to move. So we're moving backwards. Now we're about 2 teeth away, or a tooth away actually. And boom, there we go. Right at our starting point. That phaser there, I would say, is working good and proper, which is odd because we're getting a lot of our noise from the exhaust area. Now if we go to our next activation point, it's actually held a little bit longer, as you can tell here. Let me just zoom in. So this point, I held it a little bit longer. I want to check towards the end of the area. I want to see what our max movement was. If you remember, in this area, it was about 7.5 teeth. So I just want to see if that's our full motion. Let's go here towards the end and take a look. And so here's a good area. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So now we had about one more tooth full of travel. So yeah, it's moving. It could definitely move a little bit further, and this is towards the end. So let's go backwards. If we're still at about 8.5, then we know that's where we tap out. That's our full range of motion, which would be, let's see, I need to find the gap. Right here. So 1, 2, 3, 4, 5, 6, 7, 8. So yeah, I would say it's not fully yet, about, let's call it 8.5, but we've reached the 8th tooth, and looks like just a little bit more. So I would call that our full range of motion, and we know we can get back to our starting point. So again, odd, but it looks like our phaser is working despite the noise coming from that area. And lastly, we'll do the same thing with our intake. Now we do know that noise-wise, we're not getting much being picked up near the intake area, and we did hear an engine noise tone change when activating the intake, as well as we did with the exhaust. So most likely, I bet we will see movement with the intake cam, and so not to drag it out too much. Let's just quickly see. So we'll flip-flop these. Let's bring up that one up here a little bit. We do need to try to find a reference point. So let's see. So a good reference point is we'll use this first big tooth uprise. Looks like, again, we're 1, 2, 3, 4, 5. We're about the 5th tooth before activation. So let's see where this point moves in relation to that gap. And so we will go over. Let's see, let's bring this up this way and zoom in here. So let's go over. So here we go. Now we're moving towards the left. We're by right about the 2nd tooth. So we have movement. There we go. And so here on this next cycle, let's go this way. We've traveled through the gap point, almost touching that tooth there towards the left. So it's traveling towards the left, so it is advancing. Let's go again. We're past that first tooth. And I just wanted to zoom out here. That is where we passed our first tooth. And that's still moving in advance direction compared to that last cycle. But if you look, we've stopped electrically activating the solenoid, but there was still oil left in there to finish giving some last pushes there towards the advancement. So that's the next cycle. After we stopped activating, it still pushed it a little bit more towards the left. And let's take a look at the next one. So right away we start dipping back towards the right once oil flow has stopped. So again, let's see if we get back to our, I think it was the 5th tooth, which it sure does look like it has there. Let's try to zoom in a little bit. So yeah, so again, just like the exhaust one, it seems to have been able to move. This one goes in advanced and then returns to its starting point. And out of curiosity, I want to see, again, the second activation was held longer. Let's see how far it moves. And just to get an idea of our full motion. So right here, the uprise in that first of the big teeth, we have crossed the gap point. Now we're in the teeth towards the left, and we are now 1, 2, 3, 4, just over 4 teeth over past the sync point. That looks to be like our full motion. And let's see. Okay, that very next one we stopped. So let's see. Right away we're on our 3rd tooth, so it's starting to go back right there. So that, I bet, is our full motion, since at this point after activation it starts draining or going back. So our full motion is to reach that 4th tooth after the gap. So intake phaser, obviously definitely in good condition. Low noise level area, along with good movement and returning point. Exhaust, though, again, oddly enough, seems to be operating correctly as far as the phaser. We just need to figure out what's going on with the source of the noise. Alright guys, so here we are at the end after repairing it. I'll try to throw up some pictures of some of the work that was done. To verbally explain. Obviously it got a timing chain. As you can see in the pictures, that the chain was stretched, and it looks like that's where all the noise was coming from, being that our phasers, cam phasers, were not uncontrollable during cranking or startup or running. And we can see that in our cam sensor waveforms for both the intake and exhaust, despite the fact that it sounded louder on the exhaust side. But I'll throw up a video showing. Video showing a lot of the slack look to be over here on the exhaust side up by the gear. And so I think that's where a lot of the noise derived from, which, yes, can be confusing, making it look like the phaser possibly might be the rattle noise. But after testing and actuating, advancing and retarding the phasers, knowing that they both moved when commanded, and we can see it on the waveform. I was confident in the fact that those were not cause of the noise, that both of those were not faulty. Both of them were actuating properly at this time, being that it would have been an added expense, unexpected expense to the customer. We opted to leave those there for now. Again, probably somewhere near close to an added $1,000 that they were not expecting. I'm okay with them because of what I saw when activating them. So what I do want to do is I want to at least get my known good for cam crank. I want to see and compare with our failed waveform. And I, out of curiosity, do have the noise detections again, all three of them. I just want to see that, especially here on the exhaust one where we were catching a lot of noise, hopefully diminishes and goes down. So I've got it set up to the previous waveform. We'll get the scope going and see what it does. So it's been running for quite a few minutes now. It's probably decently getting warmed up. I've got the scanner just to show you. Let's go ahead, read codes. And as you saw earlier, those codes would come back right away at crank up, start up, since it monitors without any need of doing variable control. So it's checking and tattletaling on base timing being off. And so right now we will read and no cam crank codes. So we are in time. We know 100% based off the waveform, and the code's not popping up anymore. This one I actually nicked the wire, so I got to fix the wire. We won't have any more codes. And just to show you, obviously this is a warm idle now. Let's go ahead and pause this. And this is crank, intake, and exhaust as far as noise detection. Let's zoom in. And look at that. Exhaust is looking beautiful. No loud oscillations. Intake looks good. Crank looks good. So here's a known good for what it should look like with no rattling noise from a chain that before was repetitive there on the exhaust side. So that's going to do it for this one. Hope you enjoyed the little ride we took with it. Whether it's a common problem or not sure. Don't do too many Hondas, but it doesn't matter what comes through the door. There's always a approach that you need to take, and hopefully you guys picked up something from this and you can apply it to all vehicles out there. A lot of the systems work similar in the same way. Just got to look at detailed information and do some of this testing. So thank you for watching, and until next time, that is all.